Welcome to an introduction of the mainframe as a big data analytics platform, especially the Apache Spark solution. My name is Philipp Brune from the Neu-Ulm University of Applied Sciences. Apache Spark is a framework for building enterprise-grade, enterprise-wide data analytics and big data processing applications. It has been released as an open source framework by the Apache Foundation, which hosts a vast setup of enterprise-related open source projects that are dealing with different aspects of enterprise computing. The most well-known one, of course, is the original Apache web server, but nowadays we have dozens of other projects. So Apache Spark nicely fits into this portfolio of projects. Apache Spark has become increasingly popular as a tool for building data processing applications. We must imagine Apache Spark is not mainly an interactive platform that data scientists will use to work with the data, to analyze the data and to get ideas on how data might be used for applications. But it is then the platform to implement this on an enterprise level with necessary performance and possibilities to run it really as a processing platform. So it is not, it does not feature a graphical user interface or an interactive component. It's mainly a command line environment, but it is, of course, well suited for writing applications and running them on a server environment. The Spark framework, or the main purpose of the Spark framework, is to improve data processing speed and throughput by in-memory processing. And therefore, it provides a core functionality called the Resilient Distributed Datasets, which RDDs, which is sort of the core of the Spark framework. And these RDDs are in-memory representations, objects of data that can be loaded from various data sources, and persistent storage may be a Hadoop file system underlying Apache Spark. So Spark is built on top of the Hadoop file system. Or it can be any other kind of data. It can be NoSQL databases, it can be classical relational databases like, for example, DB2. It can be files, flat files, it can be unstructured data, it can be data from the internet, streamed data, and so on. So everything that can be loaded by respective adapters into the RDDs and then be processed with support of in-memory. Second thing that RDDs do, resilient distributed datasets, is they split the processing in a cluster or in a grid on multiple computation nodes. And on top of this, Spark provides different libraries for implementing data processing on top of the RDDs, like, for example, an SQL layer that allows to access RDDs in a way that is similar to classical relational databases, streaming layer, or very important, the so-called MLib, the machine learning library, which implements the common algorithms for machine learning, like artificial neural networks and support vector machines and regression and all these things. So it's a tool set for implementing most standard machine learning and artificial intelligence algorithms using the RDD for improved performance. And then we have a similar thing for graph data processing, which is not so common maybe. And then we have on top a more recent API they call the Data Frames API, which is sort of a abstraction on top of the other concepts that simplifies programming. And the programming itself, as I said, it's not an interactive tool in a way that you have a GUI for working with the data, but you program your data processing using normal programming languages, and Apache Spark provides support for Scala, Java, Python, and the famous R language, which is used very frequently by data scientists. So you can work in these typical languages that are popular at the moment. Spark framework itself is written in Scala, and Scala is a language that a functional language that compiles to the Java virtual machine as well. So you can mix it also with Java. So Java and Scala are sort of natural languages to be run on this framework, but the others are supported as well. And this framework, as I said, is open source, so it can be basically run on any platform that has JVM support. But we already learned that the mainframe has a very high performance Java virtual machine, so it is very well suited to run these kind of applications. And Apache Spark on the mainframe runs on Linux, of course, and as well on ZOS in the Unix System Services environment using the mainframe JVM. So a basic feature of this Spark core is, as I said, this implementation of the resilient distributed datasets, which provide not only in-memory calculation, but also to split large datasets on multiple nodes, on computation nodes, which can be servers in the grid or computers in the grid. And the architecture is always in that way that you have a central master node, which is called the Spark driver. This is the node that the programmer actually interacts with, or that actually executes the programs that the developer provides to the system. And these programs are run here, and then the Spark driver are executed here, and internally all the operations from the Spark libraries are then split up on the worker nodes. And the data is also split among the worker nodes. As you can see, a single RDD, here for example RDD1, can reside on multiple nodes to make it scalable for large data amounts of data, and the processing then is also split among the nodes. So Spark provides transparent functionality for splitting the calculation on a cluster without the need of defining that by the developer, and of doing that in the background. And the data may be split as well, so that a single RDD resides on multiple nodes, and also different RDDs can reside on the same node. As you see here, for example, we have here parts of RDD2 and 1 on one worker node. After the calculation, the data is collected again, and the Spark driver sort of gets back the results and combines them to, for example, for output. So on this slide, you see a simple example how such a Spark program would look like. I used a program that basically uses a multi-layer perceptron, an artificial neural network, to analyze some data. This is a Java program, but the program in Scala or Python would look the same, because the classes and the API is of course the same, just with a different style for the respective programming language. Every Spark program needs to first initiate a so-called Spark session, which is here stored in the variable Spark. This Spark session is basically like a connection to the Spark system. It represents the Spark system, and then you can use that for making API calls. And the next set here, the data is loaded into data frames, and you can see here the data frames. And then the data is split up into a part that is training data and test data. So of course in reality you would have different data for training and testing, but this is just a test program, demo program. And then the network is defined with its layers. This array here defines the number of perceptrons per layer, and then the network is trained with the training data part and tested with the test data part, and at the end the accuracy is calculated and put out of the prediction that the test data would achieve with the trained model. So that is basically the idea. I think when you read it, you see the different steps, and this is more to show how such a Spark program would look like. So you see it's really a program, it's not something interactive, it's really processing that has to be defined and that actually can be used to build data science and AI solutions for large-scale sets of data. And this, of course, is a typical task that mainframes, a typical workload that mainframes are made for. And this is why, of course, Spark is an interesting technology on the mainframe. So IBM is strongly supporting Spark on ZOS and Linux on the mainframes, and they also provide special add-ons that are commercial add-ons. As I said, Spark itself is open source, but IBM provides, of course, a commercial version for ZOS, which has support and enterprise support, and also adds different components that are used, for example, to access the mainframe and the ZOS style data. For example, DB2, you can see it here, it's this access layer here, which is added, this access component. And it allows, for example, here to access different mainframe style data sets like vSAM data sets on ZOS, DB2, and online transaction processing data from KICS and so on. So this is tightly integrated into this extended version of Spark that is especially useful for processing on ZOS. And of course it has connectors for accessing other kinds of data, internet data and social media and all the RESTful APIs and so on, what we have today, but it has special features for accessing classical mainframe data, like data sets, partitioned data sets, and vSAM data and so on. And this solution is packaged as a Apache Spark on ZOS, and this is something that is unique for the mainframe platform. And of course you could ask why this is special, or why is it meaningful to run Spark on the mainframe. And the answer to this there are different answers. Originally, Spark was developed to scale horizontally on a cluster. So it is, by its heart, it's an approach to split processing on multiple nodes and collect the data afterwards, again, using in-memory techniques. So, of course, the question is why this technique from a approach where you have a horizontal scale out, to move it to a classical mainframe environment where you have a vertical scaling, of course, is something that needs to be discussed. And the reason for that is that in a vertically scalable environment like mainframes, you reduce the admin overhead for setting up the cluster, of course, because you can basically run everything in one big node, making it much easier to maintain and achieving a similar computational power. And of course, you reduce also the overhead for communication that is necessary in a cluster, because you can run it inside a single box. And this, of course, is an improvement in some scenarios. And security is also improved because the data does not have to sort of move over a network, and it remains inside the box, so it has some advantages as well. And of course, the mainframe hardware itself is optimized for such kind of highly vertically scalable data-oriented workloads with its I/O subsystem, the channels, and the high number of CPUs that can simultaneously access the main memory and so on. So the mainframe is very well suited for data processing. And of course, if you look at analytical applications in an enterprise context, it is very interesting to have the analytical processing there where the data already is. And the data, typically the core data of an enterprise, resides on the mainframe for large-scale enterprises. So there you have the DB2 instances, there you have all the traditional workloads, you have all the structured data. The core business data is residing on the mainframe, and if you do the analytics there, you don't have to move around and copy the data, but you can directly access it where it is. And of course, other types of data that may originate from other kind of applications, from the internet, from streaming, unstructured data, videos and graphical data and so on, they might be loaded to the mainframe platform, but the core business data is already there. So that is an advantage as well, because it avoids copying, duplicating data that's not necessary, and it allows a very quick access, because these additional components have a highly optimized access, for example, to a DB2, because they run inside the same box and don't need to use a memory network connection. They can use in-memory techniques to do that. So Spark is a very promising and interesting platform to be used on ZOS especially, and I guess we will see many interesting applications regarding data science and data analytics in the next years that make use of these mainframe capabilities. Thank you very much.